Sir, good morning, sir.
Sir, good morning. Yeah.
Sir, shall we start, sir?
Yes, sir. We can start.
Okay. Thank you, sir. Unganadu College of Engineering and Technology to AICTE sponsored 2 weeks online faculty development program. Mixed signal processing for fourth industrial revolution. So today our resource person, Mr. Samuel Jigme Harrison, ST Microelectronic Singapore. Welcoming, sir.
Thank you, sir, for the invitation and the opportunity to be part of this program.
At the session, a small introduction about today our resource person, introduced by Mr. Bhaskar.
Very pleasant morning to everyone gathered here. When life puts you in a tough situation, don't think why me, just think try me. This line is more suitable to our today's resource person, Mr. Samuel Jigme Harrison. Before going to session, let me see the short intro about her. Samuel Jigme Harrison started his engineering education from St. Joseph College of Engineering, Chennai, with a bachelor degree in the field of electronics and communications between 2004 and 2008. He then completed his master's in science, specialization on integrated circuit design, a joint degree from Nanyang Technological University, Singapore, and Technical University of Munich, Germany in 2010. He also holds a master's in business administration from Anglia Ruskin University, UK. During his studies in these three institutions, Samuel published journals and papers in different conferences and national level symposiums. Samuel started his career with the Avago Technology Singapore in 2010 as an entry-level IC design engineer. He then got promoted as a senior ASIC design engineer in 2014, and the company was renamed as a Broadcom Limited Singapore in 2016. Samuel is currently working with the ST Microelectronics Asia Pacific Private Limited, Singapore, since 2017 as the Senior Digital IC Design Engineer. He has 10 years of experiences in a VLSI, specialization in physical design implementation with the 90 nanometer, 65 nanometer, 40 nanometer, 60 nanometer, and 7 nanometer technologies, and cover areas like a floor planning, place and route, clock tree synthesis, static timing analysis, and physical verification. Samuel received a technical merit novel approval in a security implementation and a clock tree synthesis using a ICC2. He has also published an article titled The Importance of Security in IC Design by the Singapore Semiconductor Industry Association, the technical magazine of Singapore Semiconductor Voice in May 2019. His membership in a technical societies like Indian Society of Very Large Scale Integration Education as a fellow member, and members in the VLSI Society of India, Semiconductor Society of India, the Institute of Electronics, Information and Communication Engineers Japan, the Institution of Engineers Singapore, Engineering New Zealand, the Internet of Things Community IEEE, and IEEE Solid State Circuit Society, and so on. In this way, now I'd like to hand over the session to our research person, Mr. Samuel Jigme Harrison, without wasting the time. Please, sir.
Thank you, sir, for a brief introduction. Once again, good morning to all the participants of today's webinar, and I hope that this session will be useful to each one of you. Let's move on to today's session. Okay, so the topic for today's discussion is physical design and its role in the semiconductor industry. Okay, so before moving on to the topic, I would like to give some introduction about the semiconductor industry in Singapore. The first semiconductor organization was opened in 1968, and Singapore houses more than 60 semiconductor companies, which employs around 35,000 people. So it is a very big industry in Singapore, and it also contributes to 7% of the country's economy. So government puts in lots of efforts to build up these industries, and most of the big design centers, design companies have Singapore as their Asia Pacific headquarters. So my workplace is ST Microelectronics. This is Europe's largest semiconductor chip maker and one of the world's largest semiconductor companies with its headquarters at Geneva. And we serve around 100K customers around the globe with 11 manufacturing sites. And we have around 46,000 employees worldwide and 18,000 active patents. So in Singapore, ST Microelectronics is a very old company, and Singapore is the Asia Pacific headquarters for ST Microelectronics. Okay, so now moving on to today's topic, which is physical design. So physical design is actually a process which transforms digital circuits into physical layout. So the front-end team who works with VHDL Verilog codings, and that circuit representation is converted into physical layouts. So a connection in the netlist, say from A to B, is converted into a physical layout where the connection between A to B is through a metal layer. So the circuit representations are converted to geometric description of shapes with various metal layers. And when they are manufactured, these metal layers will ensure the same functioning of the circuit. Okay, so this is actually the IC design flow for digital IC design, where you have a system specification. Architectural design is where the architectural team works to come up with the design based on the customer's request. And then we have the functional design and logic design portion, and the circuit design. So all this is a front-end part. And then it comes physical design, where you have partitioning, floor planning, placement, clock tree synthesis, signal routing, timing closure. So today we will be looking into each step in detail. And next is physical verification and sign off, and followed by fabrication. So from fabrication, it is the role in the manufacturing industry where they manufacture the chip, then the packaging is done. So when you see a chip in any device, you will be able to only see a black case with few pins on both the sides. So the black casing is the packaging, and then the testing is being done to make sure that the chip works. So how does this testing happens? All the pins external, which is outside the casing, is being connected to the board to make sure to check it works. Okay, so the inputs to physical design are a netlist, library information of cells in the design, a technology file with the manufacturing constraints. So this technology file is technology dependent. For 40 nanometer, we have a separate file, and the 65 nanometer, we have a separate file, and this is provided to you by the manufacturer. And we have the timing constraints. So timing, power, and design constraints are to be met during physical design. So this is the main criteria where we check for timing, we check for power, and we check for the design constraints like DRC and LVS to be met. Okay, so the main steps in physical design are floor planning, power planning, placement, clock tree synthesis, routing, static time analysis, and physical verification. So today we'll be going through all these steps in detail. Okay, first one is floor planning. Floor planning is a critical and first step in physical design. So what are the goals of a good floor plan? You have minimized total chip area, routability of the design. So the design should be routable. So we need to come up with a floor plan which is routable and which has minimal congestion. So only when you have minimal congestion, your timing will be easy to achieve, and also you will have low power consumption. So when you have minimal congestion, what happens is you will have less efforts to timing closure. So when you say less effort, it is like you add less number of buffers and inverters that are designed for optimization. So when you add less number of buffers and inverters, automatically your power consumption is low. So because all these buffers, inverters, clock buffers, clock inverters, they contribute to power. So as you keep the numbers of clock inverters, clock buffers, normal buffers lower, your power consumption will be less. Okay, so what are the steps in floor planning? So first is we determine the size of the step, we determine IO pin placement, we determine macro placement, and we create standard cell rows, and we add routing and placement blockages. So we will look into this in detail. First one is the size of the chip. Floor planning can be controlled by following two parameters, which is aspect ratio and core utilization. So aspect ratio is nothing but the width to height ratio of the chip. So width can be related to the horizontal routing resources, like the areas where the horizontal routes appear, and height can be related to vertical routing resources. So your aspect ratio is equal to the number of horizontal routing resources by number of vertical routing resources. So if your aspect ratio is 1, then the block shape will be a square. And if your aspect ratio is greater than 1, then the block shape will be rectangular with more routing resources in the vertical direction. So your height is greater than the width. And if your aspect ratio is less than 1, then the block shape will be rectangle with more routing resources in the horizontal direction. So your width is greater than your height. So if you see the figures below, 1 is AR is equal to 1, and AR less than 1 is 0.5, AR greater than 1 is 2. Okay, next is core utilization. The area occupied by the standard cells, macros, etc., and that is a percentage of area used for cell placement. So when you calculate the utilization, we need to first come up with detailed step where you calculate all the X and Y of the macros being present, the IPs, and the standard cells you're going to put it in the standard cell area. So based on that, you need to calculate the core utilization, which is the standard cell area plus the macro area, because the macro area is fixed in the floor plan, because you know the number of macros, the type of macros, the size of the macros, so you can calculate the macro area. And once you have the macro area, the rest of the design is for the standard cell. So this one by the total core area. So if your core utilization is 0.6, for example, it means like 60% is already used for cell placement and only 40% is left for routing. So if your core utilization is 0.7, then 70% is used for cell placement and only 30% is for routing. So where your routing resources are less, and it may result in congestion and timing issues. So the best practice is to have a core utilization between 0.5 to 0.6. And core rows. The height of the standard cells determine the spacing between the core rows. So the standard cell will have an X and Y. So the Y will contribute to the height of the height of the core rows. And we need to make sure that alternate rows are flipped to change the row orientation. So this core rows are the rows where during placement step, the tool will place the standard cells. So when the tool places the standard cells, the top part of the standard cell or the bottom part will have either VDD or ground. So when the tool places it on the standard cell, the VDD of the standard cell and the VDD stripe in the core row should match. If your VDD of the standard cell is placed on the ground of the core row, then what happens is it creates a short. So in order to avoid it, when we flip the rows, the orientation of the cell changes and it neatly places the VDD of the standard cell on the VDD of the core row. So this is to avoid shorts. So we need to determine the spacing between the macros. So a minimum spacing must exist between macros for pin sites. For example, if your channel spacing is equal to the number of pins into pitch by available layers and total layers. So when you place two macros close to each other, we need to see the pin placement first, and you need to calculate the number of pins being placed and the pitch. Pitch should correspond to the topmost layer of two among the two macros. For example, if you have two macros to be placed next to each other, and one macro has pins in metal 4 and one macro has pins in metal 3, then you should calculate the pitch of metal 4. As far as floor planning is concerned, we need to avoid open spaces in the design to the maximum. Because if you allow open spaces in unwanted open spaces in the design, then during placement, you will see that the standard cells get clustered to only one region, and many open spaces are left in the design. So during floor planning, if we are able to control the open spaces, then in placement it will be smooth. Okay, during macro placement, the pin of the macro should always face towards the logic area, because if it faces the outside boundary towards the boundary, then during route, tool will have to create a long route. So we need to make sure that all the pins of the macros, they face towards the logic area. And we need to use a data flow diagram and a fly lines as a reference. The data flow diagram is provided to you by the customer, where they will have information of like which pin talks to which register, which pin communications, which macro, and so on. So we need to ensure that routing channels between macros is big enough to accommodate the power stripes and also the signal routes. Macros can also be aborted with the pin sites in the opposite direction. So when you abort two macros, we need to make sure that the pins are on the outward direction. Only then it will help for routing. If your pins are internal and you abort it, then you will have problems during route. Okay, so next is the blockages. There are two kinds of blockages. One is the placement blockage and one is the routing blockage. So placement blockage prevents placement of standard cells, buffers, and inverters. So the placement blockage must be used in thin spaces between macros. So placement blockage contributes a lot to the cell utilization and also placement of standard cells. So if there are thin regions, thin spaces between macros, and it is not required, we have to put in a placement blockage. The reason is, if you don't put in a placement blockage, a tool will place a standard cell in that region, and the standard cell will be placed very far apart inside some closed region. So it will contribute to lots of congestion issues and also routing problems. So we need to make sure that whatever thin spaces, small spaces, which you feel is not required for placement, you need to put a placement blockage during floor plan step. And next is the routing blockage. This prevents routing of metal layers in the blocked region. So during routing blockage, you have the facility to select the required metal layer to be blocked. So you can select a metal layer, and if you apply, then the blockage for that particular metal layer is being put in that region. Okay, so this is actually an Innovus GUI. So for physical design, we have two basic and more prominent tools. From one is Cadence and one is Synopsys. And from Cadence, we have the tool called Innovus, and from Synopsys, we have the tool called ICC2. So this is how an Innovus GUI will look like when you open a design. You have a toolbar at top, which has file, edit, open, everything. And you have all these icons at the bottom where you have open, save, you can select, deselect, zoom, and everything. And at the bottom also you have a ruler, you have a wire, net drawing facility, you have an option to cut a net, and so on. So this is actually a design view. You are able to see the design in few views. And here you have a layer control bar where you have the ability to enable, disable like standard cells, instances. You can check the placement blockage, routing blockage. If you click this plus button, it will drop down a menu for you to select a placement blockage, routing blockage, and here you have a congestion. So when you click congestion, you'll be able to see the congestion map. And here you have all the layers, required layers. You can disable, enable each layer to debug. So main purpose of this is to make sure for you to check whether your design is properly routed, and also to fix DRC violations, spacing violations between metals, and also to analyze timing issues. So at the bottom, you have a routed status. So this design is routed, so you see a routed status. And you have coordinates. So when you keep your cursor, move your cursor to some region, this coordinate will change. And also you have a query button. And here you have, when you click this red color net, which is metal 2, when you click it, the net name will appear at the bottom. And also at the top, you have some details. So this is actually when you open a design, the name of the design will be displayed at the top. So this is actually very important for you to make sure that you have opened the right design when you want to fix something, when you want to debug. So when you open a design, the first thing you need to make sure you check the top caption to make sure that you have opened the right design. Okay, this is how a routed design will look like, where you have pins at top, and each pin is being routed and connected to different metal layers. Here you see at top you have metal 1, and here it converts to metal 2, and it gets connected internally. So around the macros, around the IPs, you have this thick metal strip, which is ground and VDD. So ground at top is a metal 1, and the side one is in red. So here if you see that this small blue line on top and bottom of this cell is the core row power connection, and you see at top it connects to ground, at bottom it connects to VDD. You see here this is the connection between this ground and the core row. So you see that there is a structure here. So when this metal 1 gets touched on metal 2, the 2 will automatically will draw a connection here. So this connection is known as via. So via is nothing but an interconnect between metal 1 and metal 2. The same thing, if you extend this blue line here, it will not create a connection. The reason is this is actually a ground net. So this ground net will only get connected to a ground net. So when you even extend it here, the tool will skip this connection. So this is how this physical design routing works. Okay. So this is actually placement of macros. Here, if you see, there are a few macros in different colors. So these macros are grouped together to make sure that they all communicate within themselves, and also they all communicate to a common clock group. So it is easy for the tool for routing. And when you do this kind of placement, you see that you have more space in the center for the standard cell placement. So we need to always ensure that the macros IPs are always placed at the boundaries of the chip. Okay, so next step is power planning. Okay, so usually floor planning and power planning come together. And what are the goals of a good power plan? To make sure that the power mesh is properly created and all the standard cells and macros have enough power supply. And only when all the VDD and ground of the macros, IPs, standard cells are properly connected, then there will be low IR. Okay, so what are the power plan components? First is block ring. So block ring is being drawn around each macro IPs, and core ring is drawn at the boundary. and we have routing standard cell pins, which I showed you here is this one. This is the standard cell pins, the routes. And next is we add the VDD and ground stripe in the core area. And next is connecting pad pins, connecting block pins, and global net connections. So all these are the important components of power planning. I will explain to you in detail in the forthcoming slides. So first is power pads. These pads actually supply power to the chip. So the power is connected to the vertical and horizontal metal stripes. So what are the power pads and what is the use of it? Power pads is each chip will have one ground and one VDD pad. So the main usage of this pad is to make sure that when the chip is being placed later after tape out on a design in a board, we need to ensure that the chip gets proper power from the board. So what happens is when we have this VDD and ground power pad in the chip, the tool when the power is been given to the chip from the board, what happens is the connection is being made to the power pad. So when the connection is being made to the power pad, both VDD and ground, the chip will get its power. So that is the main reason why we need power pads in the design. And next is the block power rings. These are blocks, power stripes around the macros. And in ours, there is a special feature to place these block rings. The width of the power stripe and spacing between the power stripes are calculated by the designer. Okay, horizontal and vertical power stripes. The VDD and ground power stripes run over the entire section of the die. So later for an example, I will show you how is this VDD and ground power stripes created and drawn. And the horizontal wires are known as stripes, vertical wires are known as trunk. So we need to ensure that the block rings, the standard cell power rails, and also the power pads are properly connected to this VDD and ground power stripe. So this one, all the power planning works like a hierarchy where initially the first step is you create power rings around the macros, and then you get your standard cell properly connected to the follow pins, the VDD and VSS for the standard cell rows, and also all the macros VDD and ground are properly connected. So it is actually works as a hierarchy. It starts from bottom and then it goes one level up, and finally the whole structure is being connected to the VDD and ground power stripe. So these power stripes actually use the highest and widest routing layer. The reason why we use highest layer is, for example, if you have 6 metal layers in your design, metal 6 is used for these power stripes. The reason is when we use higher metal layers, their resistance is low, and also more current flows through these power stripe. So it helps the chip to achieve a good power. Okay, standard cell rails. These rails are actually used to supply power to the standard cells, and they are connected to the rails through the follow pin. So in the route step, in an interactive GUI session, there is an option for you to create the follow pins. So the follow pins are either in M1 or M2. The row orientation, as I mentioned earlier, of alternate rows should be flipped so that the VDD and the ground are properly aligned from the core rows with the standard cell cells. Okay, so next is IO pad placement. IO pads are very important components in the chip, and we need to ensure placement of sufficient number of VDD and ground pads on either side of the chip for uniform power distribution. And power dissipation and IR drop should be taken into consideration while deciding the number of VDD and ground pads. So the main focus in the physical design in today's world is to ensure that we achieve a power low as possible. So because now the designs are quite small, because as technology shrinks, the components are very small in size, and the companies are too worried to make sure that the chip has low power consumption so that it is not heated up. So next is power connectivity from ground and patch to the entire area of the design should be properly checked. So we need to make sure that all the VDD and ground pins inside the floor plan should be connected to power. This will actually help you to bring down your power consumption and your IR. Okay, so this is actually a pictorial representation of power planning, where you see power pads on either side, and then you see trunks, and also you see stripes. Here you see the standard cells core area. So at the boundary is the core IO boundary, where you have VDD and VSS, and all these VDD VSS are internally connected. You see here there is a connection for VDD, and it actually is being connected to the standard cell rows. Same thing for VSS, it is connected to the standard cell rows. So this happens in power plant. So it is actually a hierarchical process where all minor things are connected upwards, and then it finally reaches the top. Okay, so this is how a block ring will look like once it is created. And this is how it looks like when you create the metal stripe. So you have a block ring here, and then you create metal stripe so that it is just to strengthen the power. And after that, you add the follow pin, where you see that the power rail, standard cell power rails are properly connected to the chip, the block. So this is how a complete power plant design will look like. Okay, so the next step is placement. Okay, so placement, what are the objectives of a good placement? Okay, the main objective of good placement is timing and power. So this has been emphasized a lot in physical design, that your timing, power, and area should be less. So you also check for cell density and pin density, which has to be minimum, and your design should be routable, and you should have a good control over congestion. Okay, and you also need to have minimum timing DRVs. These are the objectives of a good placement. Okay, the placement step is divided into three parts. First is global placement, second is legalization, third is detailed placement. Global placement, it takes about 50% of the runtime. So there are no special buttons for global placement, legalization, and detailed placement. So the log file, all these runs are internal to the tool. So you will not be able to see it unless you check the log file. So the tool here finds an approximate location for the cell based on timing and congestion. So what happens is global placement is all the cells are being placed in random in the design, so they will do overlap with each other and they do not align with the power rail. But this global placement is very important because the tool, based on its ability, it will try to arrange the cells in the design. So cells will overlap with each other, and later during optimization, it will be better. So this placement technique is quite fast and is accurate for the initial timing and congestion analysis. Okay, this is actually the image after global placement, where you see that the standard cells are not properly placed on the power tracks. You see the standard cells overlap with each other, and all this is a best example for global placement. next is legalization. Legalization is a very important step in placement because the tool moves all the unwanted overlaps and it fixes the legal locations for the cell. So all the overlaps are eliminated in this legalization, and cells are also aligned to the routing tracks. So cells connect to power and ground rails. So the final step is detailed placement. So this actually occupies 50% of the runtime. So in detailed placement, this is nothing but a step where minor modifications occur in the locations of smaller modules. So here in detailed placement, it is like refining the placement, fine-tuning the placement. So the placement is already complete in legalization. So this is actually just fine-tuning of the design. Okay, so placement bounds. This is actually a very interesting feature where you have the ability to control the placement of a group of standard cells. So for example, if you have 10 macros and 10 memories and they communicate with few standard cells. So when during placement, if we allow the tool to do the placement, then the tool will place these standard cells in different areas. So it will not force the tools to place the standard cells close to the memory. So what we do is, in order to get a good placement, we club some standard cells together, and during placement, we will ensure that these standard cells are placed close to the pin. So in this procedure, you will be able to close your timing at a very early stage. Okay, the next one is addition of spare cells. Okay, so what are spare cells? Like, for example, we take this phone, iPhone 10, and iPhone 10 is working fine, and you have completed a design for iPhone 10 and it looks perfect. Next is the company comes with a feature, and we may release iPhone 12. So when the company comes with the feature, they will come back to the designers and they will request you for adding this change in the design. So when you want to incorporate their request, what you have to do is you have to modify the netlist with maybe modifying the AND gate or NAND gate, etc. And you have to make sure that you are able to place the new standard cell in the design. So in order to place the new standard cell in the design, we need to have a cell called spare cell. So only when you have spare cells, the company will be able to remove the standard cell and place the new cell. But what happens is, if there are no spare cells, then if the company comes with a recommendation for iPhone 12, what happens is you won't have any space left for accommodating the new cell. But you cannot also remove any cell in the design in random, because they are all connected in the netlist. So in order to avoid all these confusions, you need to make sure that you have these spare cells added throughout the design, so that you are able to access the design, fix anything even at the later part after tape out. Okay, so this is an example of good placement and bad placement. Here you see good placement, the fly lines are properly connected and the cells are properly placed, and you can see that the pin locations are perfect on all sides. Whereas if you see the area for bad placement, the bad placement is where the pins are clustered together, and also you can see the fly lines, the pin cells are not properly placed. So all this is contributing to bad placement. Good placement and bad placement. So in good placement, we see a decrease in area and length of wire, whereas in bad placement, we see an increase in area and length of wire. So in good placement, your routability is very easy, and in bad placement, your routability is difficult. And you have shorter wires. So the shorter wires contribute to less power consumption, and longer wires contribute to high power consumption. So next is your hotspots. So soon after placement step, we need to check for hotspots. The design, we need to run redoc and check how is the status of the chip, how is the connection and everything. So when you have no issues, no congestion, your hotspot will be less. Whereas if you have more congestion, more issues, your hotspot will be more, and it will lead to degradation of performance. So we need to make sure that we always get a good placement. So how do you get a good placement? We need to have a good floor plan. So in physical design, each step is interlinked to each other, and the output from the previous step will be the input for the next project, and so on. It goes with. Okay, congestion is the next important feature. So congestion occurs if the number of available routing resources is less than the required routing resources. Yeah, so congestion occurs if the number of available routing resources is less than the required routing resources. So we need to make sure that in each step of physical design, your congestion is as low as possible. So only then this will help you to achieve proper DRC closure and timing closure. So a congestion map is available in the GUI in the interactive session of Innoverse. For each step, you can click, open it, and you'll be able to see where is your hotspot. Okay, so what are the reasons for congestion? High standard cell density, it creates hotspots, and if the standard cells are clustered together in one particular region, it will create hotspots. So we need to make sure the standard cells are properly placed, and there is proper placement, and there is a guideline for placement. And no proper placement blockages will result in congestion. There are less routing resources. Placement of macros in center of the chip instead of boundary. As I mentioned earlier, we need to always make sure that the center of the chip is allowed for standard cell placement. And one major reason is the tool does buffering during I/O placement. So during optimization, the tool will add buffers, inverters, which will actually contribute to congestion if this design is complicated. Okay, what are the strategies to fix congestion? You need to identify areas with low utilization, and you need to modify the floor plan accordingly. You can spread out the top level ports or move it to other sites, and increase our spacing between macros, any proper blockages to be added, and block resizing to reduce overall congestion, and also macro pins should face towards the logic area. So here, if you see that your standard cells are placed, and you are able to see that internal to the standard cells, the route is complete, and you can see their connections. Okay, so this is a trial route. Trial route is nothing but when you run placement step, the tool will come up with a trial route to show like how is the placement being done and how is the progress so far in terms of congestion and routing. So this is not a proper route. Proper route happens only in the route step. So this is actually a trial route for you to understand and see how is the power, how is the placement of standard cells, and how is the routing in the design. Okay, so next step is clock tree synthesis. Clock tree synthesis is a very deep subject, and it is very important for each role in physical design. Okay, so after clock tree synthesis, we'll be having routing, and after routing, we'll be having static time analysis and physical verification. So clock tree synthesis. This is actually an image before clock tree synthesis. What happens is you have a clock here, and this clock actually is being driven by all these flip-flops. So when this clock source communicates this flip-flop at the end, and this clock source communicates with this flip-flop at the beginning, you can see that the difference is here. There's a huge difference in communication, right? So in order to avoid it, so when you have this kind of differences in the chip, the tool will be able to identify the paths which is lagging the communication at a faster rate, and it will actually add clock buffers and inverters. So in this path, when the tool adds like few clock buffers or few clock inverters, the distance with the distance will be brought forward. So the distance between this path and this path will be more or less the same. So it will help you for balancing your clock tree synthesis, and also it will help you for timing closure. Okay, so what are the objectives of clock tree synthesis? The main objectives of clock tree synthesis are minimum skew, minimum insertion delay, maximum transition, and maximum capacitance. Transition and capacitance is nothing but the DRVs. So main objective is to have minimum skew and minimum insertion delay. Okay. So what are the effects of CTS? During CTS, there is addition of clock buffers and clock inverters. So if your design is congested and if your placement is not good, then the CTS will result in more number of clock inverters and clock buffers. So this will actually in turn affect your power. So when there is clock inverters buffers added, your congestion will increase a lot, because the clock inverters and clock buffers are bigger in size than the normal buffers and inverters. So they will actually add to more big components, which will actually affect your congestion. Okay, so how is CTS achieved? So addition of clock buffers and in clock inverters, and we can optimize the skew to balance the clocks, and also non-default rules is applied to the clock nets. All this will help you to achieve good CTS. Okay, now is clock buffers and inverters. So you may have a question like, why do we add only clock buffers and clock inverters for clock tree synthesis? Why not the normal buffers and inverters? Clock inverters actually are used for clock tree building, and clock buffers are used for balancing. So clock buffers actually have equal rise and fall time. So that is the main reason why normal buffers are not used. So when there is equal rise and fall time, it is easy for balancing. And clock buffers are also increased in size than the normal buffers. This one I mentioned it to you earlier. Okay, now there are a few definitions for you to understand before clock tree synthesis. So first you have the launch clock in the, it goes to the flip-flop, and from there actually there is a combinational logic present in this middle, and then it again communicates with the flip-flop. So you have a launch clock, and just to make things smooth, you have a path where it is connected to both launch clock and capture clock at the same time. So that difference will give you the skew. Here you have min delay and max delay. So here you have a launch clock and a capture clock. So the launch clock and capture clock. So after the rising edge of the clock, you have a min delay, and the max delay is like one complete cycle. Okay, so this is actually I mentioned earlier that before clock tree synthesis, one clock communicates with all the flip-flops, whereas here the clock is been CTS has been done where one clock source gets split up gets communicated with other inverters or buffers to make sure that the delay is minimum. Okay, clock tree synthesis actually has been of two types. One is using a clock mesh, and one is using the normal clock tree synthesis. So previous days in those chips, they were using clock mesh, and the reason why we say the clock mesh is not advisable is even in some regions where they don't require any medical assistance, like for example, if a clock mesh, if there are certain areas where they don't have to be treated at all, like they don't have to be the skew is very good, and you don't need to add a buffer, you don't need to add clock trees at that region, then it can be avoided with the normal clock tree. Whereas in clock mesh, the tool will actually draw a mat kind of structure all over the chip. So even if there is a area where it has where no requirement for any treatment is, the tool will still have the clock mesh. So this will actually contribute to more power consumption. So we need to identify areas in the design where an attention is required, or treatment is required to fix this clock tree to balance the clock. So this can be done on a case-by-case analysis basis, and so it is like how a patient is being treated by a doctor. So wherever you see that you need to balance the clocks, in those particular areas alone, you will add your clock buffers and inverters. So this clock mesh concept is now being withdrawn in many companies, and most of the companies, they work for clock tree. Okay, so how do you achieve a proper clock tree? We pre-route the clock nets. For example, the first routing in the design is being done for the power nets. You have seen in the power planning step where you VDD and ground is being routed, and secondly, now is the clock routes. So the clock routes are given priority, and you can use the routing tracks. And also the clock nets are also routed with higher metal layers, and these higher metal layers have wide width. And also you can shield the clock nets. How does this shielding occur? You have the clock net in center, you have the clock net, and surrounding the clock net you have VDD and ground power side. So when you have a clock net, right side net will be either VDD or ground, and left side net will be also either VDD or ground. So this is how a proper clock tree can be achieved. Okay, that is a structure called non-default routing rules. So these non-default routing rules are special features allowed only for clock tree synthesis nets. So these rules actually consist of double width, triple wide metal with double wide spacing, and these NDR rules should also follow the DRC rules of the design. Okay, so after clock tree synthesis, you have a feature in the Innoverse interactive session known as the CC opt debugger. So you can open it, and when you open, you'll be able to see that the buffers, inverters added here, and also the name of the flip-flop. So here you can see that everything is balanced properly. So when you click this inverter or buffer, you will be able to see the name of the inverter, and what is the connection, and how big is, what type of inverter is it, how big is the size, and the inverter name is available. So this will give you an idea when you need some details for debugging. And here at the bottom, you will have the min delay, max delay, the skew available, and what are the pin names, and so on. With this, we come to an end of clock tree synthesis. So in today's webinar, we have covered floor planning, power planning, placement, and clock tree synthesis. The next step is routing. So we still have 3 more topics to discuss, which is routing, static timing analysis, and physical verification. Okay, so what are the goals of routing? The goals of routing are to minimize the total wire length in the design. So proper routing will enable less wire length in the design, and we will minimize the delay, minimize congestion hotspots, minimize the number of metal layer changes, because for each layer change, like you will have to add a via, so you will have to add an interconnect. So all this will contribute to more power consumption. And the best practice is to complete routing without increasing the area of the design. So this, how can this be achieved? We need to make sure that we do a good floor plan, and also placement should be good, and only then in route step we'll be able to achieve our target. So a good timing closure is also a end result of routing. Because if your timing is not clean and rest all parameters are clean in the design, still you will not be able to release your chip. And if timing is clean and you have 2 shots in the design, still you will not be able to release the design. So everything has to be clean. Okay, so we just spoke about the routing order. First, we routed the power stripes, which is the VD and ground, in the floor plan step, and now we completed the route of clock nets in the previous chapter. So clocks are given higher priority, and higher metal layers are used. The third one is the signal routing. So this happens in the route step. So the route step is only concerned on the signal routes, because by the time we reach this step, the power routes are already routed and clock nets are also routed. Okay, so there are special routing grids, routing tracks for the tools to place the metal layers. The routing grids are defined for the entire layout. Routing direction is defined for each metal layer. So for example, if M1 metal 1 will be assigned horizontal direction to be routed, and M2 is assigned vertical direction. So M3 is horizontal, M4 is vertical. So it happens like this. And when you give the route command, the tool will ensure that M1 is routed only in horizontal direction and not in vertical direction. So now if you see here, you have a design here and you have a routing track. So you have a vertical routing track and also you have a horizontal routing track. So in the next figure, you will be able to see here that there is a standard cell and there is a metal layer being drawn from the standard cell, which is metal 2. So the red is metal 2 and the blue is metal 1. And here you see you have a metal 1 connection here, and there is an interconnect. So this one is known as a via. So if you don't have a via here, even though you have metal 2 and metal 1, there is no connection being made unless the via is here, because via is the only one which connects metal 2 and metal 1. Same, it also connects metal 2 and metal 3 and so on. So a via is a must in physical design to connect the 2 metal layers. Here from metal 1, the tool again goes to metal 2. So here you have to add a via. So this is how a design will look like. Router design, and this is the basics behind routing. Okay, so what are the stages of routing? Stages of routing is same as stages in placement. So I'm sure that you remember in placement we have global placement, legalization, and detailed placement. Same as in routing, we have global routing, track assignment, and detailed routing. This is an example for global routing, where you have all the routes in the form of traces. So it is not a completed route, but it is just a trial being done to understand how is this going to impact timing. So trial route, this global routing and the route step will include will be timing driven and also crosstalk noise driven. So the tool, when it does this routing, will also take into account timing and also the crosstalk noise. So I will explain to it later. And so this is global routing. And what are the objectives of global routing? It minimizes the overflow of congestion, and it reduces total wire length and runtime reduction. Okay, so what are the types of global routing? As I mentioned earlier, it is time driven. Wire delays are calculated before global routing. So tool does all the calculation, and their configuration algorithm is based like that. And the next is crosstalk driven. So how do you avoid crosstalk? It's very simple, that when there are two long nets in the design which are parallel to each other, it will lead to crosstalk noise. So we need to make sure that in the design, two metal layers do not travel for a long time together. Like it is better to avoid two long nets in parallel on the adjacent tracks. So you can cut the metal layer, you can do a zigzag pattern. Okay, tracking assignment. This is the second step where the tracks are being put in, are assigned for each global route, and assigning horizontal and vertical tracks depend on the metal layer. So in track assignment step, all the overlapped wires are rerouted. Same thing happens in legalization in placement, where all the overlapped cells are properly placed. So here also it is the same. So this is detailed routing, where this is a final route, and you see that the routes are properly drawn by the tool. So all these steps are internal to routing, and when you just select nano route or the route step in the GUI, all these steps are not visible to you, but it will be available in a log file. So we need to ensure that we always check the log files for each step once it is complete, to make sure that there are no errors and no warnings. And we need to ensure that the process is smooth. Okay, so this is actually a congestion map after routing. So if you see that there are blue spots all over the chip, so this one actually is nothing but it is less congested areas, and in the middle there is yellow spots and red spots. So the red spots actually are the most congested area. So we need to highlight this, zoom into this location, and see what went wrong and how this hotspot can be improved. So if we don't fix it, later during power analysis, this same issue will be highlighted as hotspot. Okay, so as I mentioned earlier, the crosstalk noise is the signal integrity issue. So signal integrity during routing is closely associated with crosstalk. Switching signal will affect the neighboring net. For example, if the affected net here is the victim and the switching net is the aggressor. So there are two nets which run parallel together, and if the two nets switch at the same time, then this will actually result in crosstalk noise. So in order to avoid it, we limit the length of the parallel nets. It can be the same net A, or it can be different nets A and B. And also shield the special nets, an upsize driver or buffer. But usually if you limit the length of parallel nets, this crosstalk noise will be clean. Okay, so this is how a routed database will look like, where you see that all the routes are being done here. So now if you see this device design, you will be able to see that there are some open spots in between. So these open spots are actually the open spaces after cell placement. So what shall we do with this spot is we need to add filler cells. So the filler cells are actually added only after routing optimization at the end of the design flow. And filler cells are used for power rail connectivity because they don't have any function in the cell. But the main reason is to make sure that here in between it there is a hole and your connectivity is lost. So to ensure that we add filler cells so that the VDD and ground power rail connectivity is continuous. Okay, so once after you add filler cells, you are able to see here that now it is complete. So this is actually the final output of route step. Okay, so now we will look into static timing analysis. This is actually a very interesting chapter, and you will have lots of information on timing analysis and lots of definitions to go through. So this is actually a check being done in digital IC design to make sure that you have no setup and no hold violations. So this step and the next step, which is physical verification, everything contributes to testing the design which we have developed so far using the physical design flow. Okay, so what is static timing analysis? Static timing analysis is one of the techniques used to verify the timing of a digital design. So it makes sure that our design meets the timing requirements. And STA can only check for timing and not the functionality of the circuit. So in the field of physical design, there are particular job scopes for STA engineers. So they should be very well equipped with all the basics of STA, which is setup, hold time, clock information, and rise time, fault time, required time, arrival time, all these delays. So they should have all the proper basic knowledge and understanding, which will enable them to get an opportunity as static timing analysis engineer. So this is how a static timing analysis engineer starts his career. Okay, so the basic definitions in STA is setup time and hold time. Setup time is actually minimum amount of time the data should be stable before the clocks activate so that the data are sampled properly by the clock. Hold time is minimum amount of time the data signal should be held steady after the clocks activate. So this one is, it will be more clear with the figure. So now you see that it's a clock path and a data path, and you see that the data can toggle in the complete region, but it will be stable before the clocks activate. So this is setup time. Same thing, the data will be stable after the clock activates. So this is hold time. So after this one, it can toggle. So this is before the clocks activate and after the clocks activates. It will contribute to setup time, hold time. So required time, it is a time required for data to arrive at a certain point. And arrival time is the time at which the data has arrived at a certain point. So these are basic definitions, which is easy to understand. And slack is difference between the required time and the arrival time. So if your required time minus arrival time gives you setup slack, arrival time minus required time gives you hold slack. And if you have a hold positive slack, indicates that the design is meeting timing. So in your timing report, if you see a condition called met, it means you don't have to fix timing. And if there is a condition called violated, then in that case you need to fix it. Okay, positive slack and negative slack. Positive slack is your required time is greater than the arrival time, and negative slack is where your arrival time is greater than your required time. Okay, so this is clock latency. Clock latency is your source latency plus your network latency. So here you have a PLL, and from PLL to the clock, the origin of the clock, you have the clock source. So this is the source latency, and from here to the flip-flop, the registers. So all this has combination logic in between. So the entire latency is known as network latency. So it is source latency plus network latency. And what is clock skew? It is a difference in the arrival time of capture edge of two adjacent registers. So there are two adjacent registers, and the difference in arrival time gives you clock skew. So we need to ensure that the arrival difference in arrival time is as low as possible, so that your clock skew is less. So when your clock skew is less, it is your timing is easy to achieve. So the positive skew is where capture clock comes late than the launch clock. Here you see the capture clock, and here you see the launch clock. So capture clock is comes late than the launch clock. Clock skew is like where launch clock comes late than the capture clock will result in negative skew. Okay, so next is a timing path. Okay, how do you understand a timing path? Timing path actually consists of three elements. One is a start point, one is a combination logic, and one is an end point. Start point is start of the timing path where the data is launched by the clock edge. So it consists of a clock, a primary input, a port, etc. Combinational logic is they contain AND or XOR elements. So flip-flops, registers, and latches are not included in combinational logic. So this is how it is structured. We have a start point, we have combinational logic in between, and we have an endpoint. Endpoint is the end of the timing path, where data is captured by the clock edge. Okay, so there are four timing paths to be analyzed. One is input port to the register, register to register, and register to output port. And one more is input port to output port. So the register to output port is based on the combination logic in between. Register to register is also based on combination logic in between, and how far is the two registers placed. All these contribute to timing violations. Okay, so how do you fix setup violation? You upsize the cell from A1 or to A2 or A6, and then you insert buffers. All these fix setup violations, and you reduce the clock uncertainty, increases delay in the clock. You fix hold violations by adding delays, detour routing, you downsize the cells, and so on. So all these are steps for you to fix the hold violation. Okay, here you have a few examples of a prime time timing report. You have a positive slack where your required time is greater than your arrival time. Here you see a start point UF11 and the end point is UF21. They both belong to the same clock group. So a path clock is I clock and path type is max. So max means setup and setup timing, and path type min is hold timing. So here you see a data arrival time 739 nanosecond, and you have a data required time of 10,000 nanoseconds. So this is just an example, and you see a slack is being met here, where your data required time is more than your data arrival time, and you have a positive slack of 9320 nanosecond. Okay, here this is actually another example where your required time is calculated by adding phase shift minus the setup plus the other end arrival time is your required time, and your hold is obtained through the flip-flops. So all these delays, inverters, DFF, INV, DFF, all these cells contribute to the arrival time. So here you see your arrival time is 0.827, your required time is 9.974. Still your required time is more than arrival time, and you get your positive slack of 9.148. So you don't have to do anything, you don't have to fix anything here. Here, this report shows violated. So there is some problem and the timing is violated and you need to fix it, and it is a hold check. So here your required time equals the other end arrival time plus hold plus phase shift and minus cycle adjustment. So this is the formula behind the required time, and your slack is your arrival time is 0.117. So your slack is arrival time minus required time, which is failing by minus 20 nanosecond. So you need to bring it to a positive slack. So all these are few examples, and but in real time we will have lots of complicated timing reports, or even if it's a simple design, we may have a very simple timing report. So this is how it works. Okay, the last step in the physical design flow for today's discussion is physical verification. So we need to verify the design with lots of checks. So first is the design rule check, which is known as DRC. The layout versus schematic check, the electrical rule check, the XOR, the logical equivalence check, so on. So design rule check is you check for DRC violations. So you check for spacing between metal layers and so on. And also layout versus schematic is to make sure that there are no shorts and no opens in the design. And also your layout is your output from the physical design, and the schematic is the output from the front end team. So both match. An electrical rule check is to check for electrical rules. XOR check is to compare databases, and logical equivalence check is to make sure that the function of the circuit is the same in physical design too. Okay, so DRC is a process where the physical design database is checked against design rules. These design rules actually are provided to you from your manufacturer for each technology. So only if your DRC is clean, or you have particular waivers for it, chip can be passed to the foundry. So what are the types of DRCs? Minimum width of a metal layer, and shorts, minimum spacing between metal layers, minimum area, then minimum width and spacing for vias, etc. Okay, this is a short here where you see that this is a different net and this is a different net, but since they are the same metal layers, it creates a short. So how do you fix this? We just move this metal, this net to here, so that there is only one crossing here, which is with this light blue stripe. So this light blue stripe and this purple stripe, when they cross, it's fine. Only thing, the same metal layer should not cross for two different nets. Okay, spacing violation. Here you have spacing violation because here you have metal 2 and this is metal 3, and here you have a VR, an extension of metal 2, so it actually creates spacing violation. So how can we fix this? We can bring this metal 3 to this region. Okay, so when you bring this metal 3 here and then you create a VR to connect it to metal 2, here you have no problem because you only have metal 3. So metal 3 is here, metal 2 is here, and that spacing doesn't matter. It's only the spacing between the same metal layers. Same thing here, you have metal 2 and here you have metal 2. So this is the spacing. So when you bring this metal 3 till here, here you will only have metal 3. So metal 3 versus metal 2 spacing is fine. Okay, so what are the basic DRC checks? We have three basic DRC checks, which is width of the metal layer, spacing between two metal layers, and enclosure. Okay, layout versus schematic check. So this is actually a schematic of a transistor, and this is actually a layout of the transistor. This is output from physical design. This is output from the front end part. So you have an extracted netlist from this PDS and an extract source netlist. So when you compare these two, the tool will generate a LBS report, and it will show you what are the discrepancies between layout versus schematic. But layout versus schematic, it should be clean. If layout versus schematic has some problem, then something has been optimized in the design. What are types of LBS errors? Shorts and opens, and also unbound pins. Unbound pins is nothing but if the pin doesn't have any geometry or layout, but in the netlist they have the connection, then it is quite risky. We need to figure it out. Okay, here it is open, where because this metal and this metal should have been connected, but it is open here. And here you see there's a short between this metal and this metal in these two regions. So if you move this metal here, it will be fixed. All these are like very basic examples for our understanding, but in real time, the shorts may be complicated, and we may not have enough resources to even fix it, because it will be jam-packed with metal layers. Okay, electrical rule check is a methodology used to check the robustness of a design. So against the electrical design rules. So we also check for floating gates, and sometimes the drain and source will be shorted. So all this is being checked with ERC. XOR check is run where the original and modified database is compared. So this is actually nothing but, for example, if you have iPhone 10 and you are the design engineer for iPhone 10, later after 2 years, the Apple comes to you and says that we need to modify few features for iPhone 12. So, and they give you a requirement that your changes should be only in metal 2 and 3, because when they redo each metal layer, it is like money for the company. So they gave you a requirement that you should only touch and make changes. You add the new features only using metal 2 and metal 3. So the front end team will get the request. They will replace. They will add the new features as a NAND gate or something in the netlist, and they will give you. And you will as an initial step, you will actually remove one spare cell and then put in the AND gate, the standard cell, and then your work is being done. And you do the routing, manual routing, because it's only 2 or 3 cells being modified. So you manually route the net. And then when you, at the end, you need to do a check called XOR check. This is actually check your initial data, the Apple iPhone 10 database and iPhone 12 database. So you do a comparison to make, this comparison is mainly to make sure that you have only modified metal 2 and metal 3, not any other layer. So when you do a comparison, the tool will generate a report showing what are the changes, what metal layers have been affected. So if it shows that only metal 2 and metal 3 has been affected, then we are perfectly fine. But if the tool shows changes have been done in metal 2, metal 3, metal 4, because when we do manual route or when we do the fix, by accident, we might have moved a metal 4 net, or we would have removed a metal 4 net. So this will get highlighted here that metal 4 is also touched. So then we are at big risk, and we need to go back to the design to see where we have touched metal 4, because the customer Apple is not acceptable with touching the metal 4 net. They have given you permission only to access metal 2 and metal 3 nets for the fix. So this is a very critical check, and it will help you to find out if there is any disturbance in any other nets than our required net. Logic equivalence check is nothing but we check the functionality of the design, because in physical design, the design has gone through lots of optimization and lots of clock steps like clock based synthesis. We have added buffers, so on. So all this has gone through, but we still need to ensure that the functionality of the design is still the same, because it cannot be like the front-end team designed the chip for iPhone 10, but when you do your physical design, the chip cannot, the function cannot be for iPhone 11. When you so both the front-end team and the back-end team should have the same functionality. So that is why we do this check where the initial RTL is given and RTL it is checked logically equivalent. All this is done by the front-end team, and the RTL modification is again converted to gate level netlist, and they check whether it is synthesized correctly. So now what happens is the synthesis gate level netlist is given to the physical design team, and we come up with the place and route netlist, which is the output netlist from physical design. And here it has gone through clock tree synthesis. We have added repeaters, place and route, lots of optimizations have happened. And even after all this, is the function still the same? This check is the logical equivalence check. So these are the basic checks of physical design. But right now, as designs have become more complicated and technology is advanced, and there are lots of loopholes. So tools have become more effective to different kinds of new checks being in the market. So each company has their own checklist to make sure that the product is good. Okay, so before we close today's session, I would just like to give some insight into life in VLSI. There are few online certification courses available both in India and US. So we can make use of them to get a brief understanding on a particular subject, and also they will have hands-on lab sessions, which is everything is online, so it will enrich our knowledge more in the deep aspects of physical design. And internships and studies are available in IITs, NITs, BITS, Bilani, top universities in India, and also we have VLSI research labs attached to the universities, and also many universities are taking up projects, VLSI projects, and they're looking for research assistants. So we can contact professors, HODs of the department, and we can write to them based on our interest, and then they will be able to help us or assign us some role in their project, which will actually give you a learning experience and also your certification, which will help you for a job. And also in abroad, we have NTU in Singapore, NUS in Singapore, GIST, which is NTU TEM in Singapore. They offer all master programs, bachelor studies in VLSI, and we have a few universities in US like University of California, MIT, Stanford University, Georgia Institute of Technology, University of California, University of Michigan, University of Texas, University of Southern California. All these are top universities in VLSI. So they have lots of opportunities, and all the details are accessible in their website, and even professors are contactable. Okay, so some job roles in the semiconductor industry. So we have design engineers, verification engineers, application engineers, and manufacturing engineers. So design engineers are like front-end engineers, back-end engineers, physical design engineers. Front-end engineers deal with the VHDL, VLOG codings, FPGA, field programmable gate array engineers, and we have design for technology, testability engineers, analog mixed signal, RF engineers, IP design. And verification engineers are front-end verification, EDA tools validation engineers, IP verification. So once the front-end design is complete, it is given to the verification team. And also the EDA tools are like Cadence and Synopsys are the EDA tools. And once a company purchases a EDA tool, they have a validation engineer who will run the tool, work on the tool completely to make sure that it is perfectly fine before the tool is given to the design team. Application engineer is for the EDA tools like Cadence, Synopsys, Mentor Graphics has their own design team and application engineers. So they have corporate application and field application engineer. Corporate application engineers are like engineers who go to the industries, to the companies, and they promote their designs promote their tools, the corporate level for business dealings. And field application engineers are engineers who actually they they go back to the companies which have purchased the tools, and they sit with them, they debug issues, and also they clarify doubts on the tools, they conduct training sessions, etc. Next is manufacturing engineer, where we have foundries and fab engineers. All these are related to the manufacturing of the chip, where you have fab manager, tech support people who take care of the tools, the machineries, and engineers who work in the clean room wearing the white dress, and they work on the step-by-step manufacture of the chip. So all these are some basic information about the roles in the semiconductor industry, and I'm sure that it will be useful for all the students, postgraduate students in the universities and colleges. Okay, some major recruiters in VLSI. We have ST Microelectronics, MediaTek. MediaTek is a Chinese company. Infineon is a German company. TSMC is a Taiwan-based, very famous company. NVIDIA is there. NVIDIA is more into graphic processors, graphic card. They have a big design center in Bangalore. Qualcomm is a very major design center which are into 5G communications, and they have a design center in Bangalore. Texas Instruments is in Bangalore, which is a US company. It's a very old design industry. Intel, as you all know, is everywhere, and they are like the world leaders in semiconductor business. And Xilinx is a US company, they are more into FPGA designs. NXP is a German company, and Cypress Semiconductor is also into VLSI, physical design, front-end design verification. Broadcom is a US company, and Broadcom has a design centers in Bangalore. Micron is also a US company. They have their own fab for manufacturing plant. And the last three companies, which are Cadence, Mentor Graphics, and Synopsys, are the EDA companies. So they are the tool companies which assist the companies at top. They are also into physical design. They also help for front-end design. They also help for timing analysis and power analysis and so on. So these are some major recruiters and some EDA companies which are into the market. So with this, we have come to a closure of today's webinar on physical design and its role in the VLSI industry. So for further queries and clarifications, you can write to me, or also you can visit my LinkedIn profile. And I hope that this session today was helpful to all the professors and research associates and staff from various colleges. And I hope that it will be helpful when you share it with your students. And once again, thanks to the organizing committee for inviting me to be a resource person for today's webinar. Thank you once again.
Thank you so much, sir. Dear participants, if you have any doubts or queries, you can ask now. Participants, if you have any doubts or queries, you can ask now. You can either post a question in chat box or else unmute yourself and discuss with our resource person.
Hello, sir.
Yes, ma'am.
Sir, this is Ilayarani from Dhanalakshmi Srinivasan College of Engineering.
Yes, ma'am. Hello.
Sir, we are going to go for placement. So is this students is prefer for testing engineers is very good, or front end engineer and back end engineer? Then go for which type of courses we are going to prefer for our students, sir?
So they are going for placement after their bachelor studies, is it?
Yeah, sir. Yeah, sir.
Yeah, so if they prefer placement in VLSI industries, either it may be testing or front-end design or back-end design,
Yes, sir.
because in our bachelor studies curriculum, we don't have much exposure or hands-on to the industry standard. So it
Okay,
is
sir.
good if they can take up some online certification courses, because at least they will have some certificate in VLSI before when they apply for some company or attend some interview, or they can also contact some professors in IITs to do some research projects, or to work under them on a research topic, to help them so that they can get used to the tool, and they will have some certification from IIT, so that it will help them to get a job. So as a fresher, it is advised that they should for sure take up some online certification courses, or they can do a master's studies for 1 year, and then they will be able to at least stand out in the market.
Okay, sir. Sure, sir. Thank you for your guidance. Thank you so much, sir.
Thank you.
Thank you, sir. I think there is no more queries from participants, sir.
Okay, sir.
Let me wind up the session, sir.
Yeah, sure.
Talent wins games, but teamwork and intelligence wins champions. In this way, I would like to thank our today's resource person, Mr. Samuel Jigme Harrison, History Microelectronics Singapore, for providing this wonderful session on the topic of physical design and its role in the semiconductor industry. On behalf of organizing team and Kogunadu College of Engineering and Technology, we once again thank you so much, sir.
Thank you, sir. And thanks to Kongunadu College of Engineering for inviting me as a resource person. And it was a pleasure to be associated with the college. Thank you, sir.
Thank you, sir. Dear participants, the day 4 session 1 attendance and the feedback link is posted in chat box. Kindly fill it in, and while filling the feedback form, kindly select your respective FTP ID. The FTP ID document is also attached in the chat box. Kindly check it. Thank you all.